Okay, so in this section, what we are going to take a look at is chemical kinetics. And kinetics is all about the study of how fast or how quickly reactions actually take place. Now, in all of your general chemistry one content, when you looked at chemical reactions, we assume that all reactions, we made some general assumptions about how those reactions happened, um, to the extent at which they occurred, etc. Now we're going to take a look to actually see that there are going to be some pretty big differences in the rates or how fast those reactions actually take place. So some reactions happen almost instantaneously, as you probably know, happen fairly quickly, whereas others do take a long time to happen. So for example, instantaneous reactions are things like explosions, whereas others that can take a little bit longer would be things like maybe iron rusting over the course of several years. So they're obviously very different in terms of their time scale. We're going to explore some of these concepts in this section. So this is particularly important, especially for industrial processes where increasing the rate or increasing the speed of a reaction is particularly important because time is money, as the saying goes, and forcing reactions to happen on a quicker time scale is often beneficial. So generally, reaction rates can be increased by doing several things. So we can say reaction, RXN are abbreviation for reaction, and then rates can be indicative of the speed. So reaction rates can be increased by doing several things. And we actually saw some of these back in General Chemistry 1. We can increase by increase the concentration of the reactants. And we're going to take a look at how these influence reaction rates a little bit later on. From a square brackets means concentration of reactants. We can increase the reaction rate by increasing the temperature, which increases the kinetic energy of the particles. We can also increase the reaction rate by increasing the surface area. So we allow more contact, in other words, between the reacting particles. And then we can also increase the reaction rate by using something called a catalyst, whose whole purpose is to actually increase the rate of a reaction. So like I said, we've talked a little bit about these. We sort of scratched the surface on some of these back in Gen Chem 1. We're going to take a lot closer look at this in this section of the course. So we can approach chemical reactions and the rates of chemical reactions by invoking different aspects of what's known as the collision theory of chemical reactions. And essentially, this is based upon several different things. So for instance, in order for a chemical reaction to occur, what we can say is, in order for a chemical reaction to happen, several things need to be in place. The reacting particles must collide. So we can say the reactants must essentially impact each other. So they must collide with each other. And that's assuming that, again, our chemical reactions are fairly simple in terms of how we approach them. Normally, when we have a chemical reaction, we have reactants on the left, producing products on the right side. Right. So in order for this reaction to happen, to produce these products, these reacting particles have to collide with each other. Not only must they must collide in the correct orientation or alignment. So in other words, if the front of one molecule collides with the back of another molecule, that may not be enough for the reaction to happen. Maybe they need to collide head on as opposed to head to tail. And then finally, when those collisions happen in the right orientation, the energy of the collisions must be enough or must be sufficient to actually get the reaction going. And we have a special name for this, which is C, a little bit down the road. Right? So those are the basics of the collision theory. And we're going to take a look at how we can affect these different things by changing the conditions to change the rate or the speed of a chemical reaction. So according to this collision theory of kinetics, chemical kinetics, we know that the reaction rate, or the rate of a chemical reaction, is directly proportional to the number of molecular collisions per unit time. So we can represent that with a simple relationship. You can see that the rate or the speed of a chemical reaction, we have a proportionality symbol, that means proportional to, and then we have the number of collisions per second. Now, we just explained the fact that collisions need to happen, but not only must they happen, they need to happen such that the reacting particles collide in the right orientation, and then they also collide. The energy of those collisions is sufficient to get the reaction going. These lead to what are known as effective collisions. Okay, so when your reactants collide, they may or may not get the reaction going. Those are ineffective, right? So in order for the collisions to be effective, they need to be in the right orientation or alignment, and then the energy of that collision needs to be sufficient to get the reaction going. So those are effective collisions that are required. So collisions that result in a chemical reaction are known as effective collisions. And we talked about the energy of the collisions being sufficient enough to get the reaction going. We refer to that special term. Well, there's a special term that we use to refer to that, and that is known as the activation energy, which is often abbreviated capital E subscript A, or E sub A is what the activation energy is, the amount of energy needed to initiate or to start a chemical reaction. So we mentioned in order for it to happen, collisions need to happen in the right orientation, and then the energy of that collision needs to be sufficient to get the reaction going. Those that do not result in a chemical reaction, those are known as ineffective collisions. Now, when a reaction proceeds, such as the one that is shown here, so for example, we have Cl, chlorine, that's an L, by the way, not an I, chlorine reacting with NOCl, so these are your reactants. The reactants on the left side. And these react together to produce chlorine gas and nitrogen monoxide. These are going to be your products. Okay, so if this reaction proceeds successfully, we should get Cl2 and NO as our products. In the example that's shown here, this was an effective collision. So we do end up with a 2Cl and NO because the collision happened in the right orientation. In this case, the Cl and the Cl actually collide together. Whereas in the ineffective collision, you see that the Cl and the oxygen collide. That does not lead, that's not the correct orientation. So it results in no reaction. We have the same thing that we started with, right? We didn't actually get any product due to that ineffective collision. So when these molecules or particles collide in an effective collision, we can monitor the reaction progress by what's known as a reaction coordinate diagram, something that you have probably seen before, where we plot on the y-axis the potential energy going up, so increase in potential energy, and on the x-axis we have the progress of the reaction or the reaction pathway. So typically, we're going from left to right in a normal chemical reaction. We have our reactants that we start with over here. These react together to produce our products that we end with on the right side. Okay, so going from the reactant to product is not just a simple case. In most cases, we actually have to get over this difference in sorry, in potential energy, this barrier or this hill, and that energy barrier, if you will, we call it that, that is known as the activation energy. That's the E subscript A that we need to overcome. So when these particles, when these molecules or atoms collide, sometimes they may collide and they give off energy or they produce energy, but the energy that they get only gets us to maybe about here. And then what happens is they fall back down, right? So we don't get over this barrier. In some cases, if the collisions are effective, then that produces enough energy to get us over this thing. We actually go through this state up here, that the top of this energy barrier or the top of this hill, the species present at that place is called the transition state or the activated complex. Sometimes you'll see that symbolized as a double dagger like this. Is often what you'll see in different chemistry books or higher level chemistry books. That's what it represents, and that's at the top. That's the highest energy state that we have in this reaction pathway, right? So this energy barrier or this activation energy is the difference in energy from the energy of the reactants over here to the energy of that at the top of that hill or that barrier or activation energy. That is the activation energy for this particular reaction. So once we get to that point, then it's all downhill till we get to our product on the right side. All right, that's your reaction coordinate where we see the activation energy or the energy barrier that we need to overcome to go from reactants to products in this particular reaction. What we also see is that when we increase the temperature of something, we increase the kinetic energy of that sample. And this is something that we saw back in General Chemistry 1. So we know that as the temperature increases, okay, the average kinetic energy of that sample increases as well, right? That temperature, remember, is just a measure of the average kinetic energy of a sample. So as the temperature goes up, the kinetic energy increases, the energy of motion of the particles, the atoms, the molecules, etc., goes up. And as a result, then we have more of a chance of those collisions that are happening. Those collisions happen with more energy, and as a result, the energy may be large enough to overcome that energy barrier, right? So we saw this back at the beginning when we summarized some of the factors that lead to differences in reaction rates. The take-home point here is that at the higher temperature, as temperature goes up, more molecule or particles are going to have higher kinetic energy, enough of that energy to exceed that energy barrier or the activation energy, and as a result, they can undergo effective collisions because they produce enough energy to get to that, to get over the hill or that barrier, right? So that's the reason why increasing in temperature generally leads to an increase in the rate of a reaction. If we go back to our example before, we saw that in this particular reaction here, or let's just use a general reaction. If I have a reaction of A and B reacting together to produce C, right? And in order for an effective collision to happen, A and B, right, need to collide in the right orientation. They need to collide to provide enough energy to get the reaction going. We just explained why an increase in temperature will lead to an increase in the rate of a reaction because it increases the kinetic energies of the reacting particles. Now, what would happen if I increase the concentration of A? Right, well, if I increase the concentration of A, guess what? I now increase the number of particles of A present, which means I increase the probability of A colliding with B. And if I increase the probability or the chances of those collisions happening, guess what I also increase? I increase the probability of those collisions being effective, and as a result, I increase the rate of that reaction. Similarly, if I increase the concentration of B, increase the number of B particles in there, I simply increase the number of collisions, and if I increase the number of collisions, there is more opportunity for those collisions to be effective, and as a result, the rate is going to increase. Okay, so that's a very generic sort of an overview look of why increasing concentrations and why increasing temperatures lead to an increase in the rate of a chemical reaction.